Good morning, students. Chapter 5, Magnetism and Matter. Yes, in last lecture we have discussed about paramagnetism, paramagnetic material, and we have discussed what is difference between diamagnetic and paramagnetic. In this lecture we will study about ferromagnetism. What is ferromagnetic material? See, the atoms of iron, cobalt, nickel and their alloys possess permanent magnetic dipole moment due to spin of electrons in outermost orbit. They have permanent dipole moment, means if magnetic field is present or not. Okay, molecule, atoms, molecule, they will have some magnetic moment. They will have some magnetic moment. Okay. Now, the atoms of such materials are arranged in such a way that over a region called domain, the magnetic moment of atoms are aligned in same direction. Now, what is meaning of this? See here. If it is one ferromagnetic material, then atoms of such materials are arranged in such a way that over a region called domain, the magnetic moment of atoms are aligned in same direction. Means if I am taking in this region, then magnetic moment of one atom, magnetic moment of another atom, of third atom, or fourth atom, they are same in this direction. In some another region, let this magnetic moments due to atoms is in this direction. In another region, it is like this. It is like this. Clear about this? Okay. Suppose in this region, it is like this. It is like this. Okay. So yes. Okay, what is meaning of this statement? See, here it is. The atoms of such materials are arranged in such a way that over a region called domain, in this region it is called domain, the magnetic moment of each and every atom, it is in same direction. So it is called one domain. It is called one domain. It is called one region. Again, in this region, the atoms have same magnetic moment in same direction. In this region, same direction. In this region, same direction. In this region, it is same direction. So these regions in which each and every atom have same direction of magnetic moment, they are called domain. So I can also draw this figure as like this. See, as in this region, in this domain, each and every atom have same direction. I can draw resultant magnetic moment in this direction. Clear about this? In this region, I can draw resultant magnetic moment in this direction. In this domain, I can draw resultant magnetic moment in this direction. On this domain, in this direction. On this domain, it is in this direction. In this domain, in this direction. Clear about this? Okay, so again understand the meaning of this statement. The atoms of such materials are arranged in such a way that over a region called domain, the magnetic moment of atoms are aligned in the same direction, Clear about this? Now, in unmagnetized sample means when external magnetic field is absent, when external magnetic field is not present. Okay, then such domains having net magnetization are randomly oriented so that effective magnetic moment is zero. Yes, in this domain, net magnetization, it is in this direction. Net magnetic moment, it is in this direction. In this region, net magnetic moment in this direction. See, each and every domain, in each and every domain, direction of magnetic moment is random. Random means if I find total magnetic moment, then total magnetic moment sigma m, it will become zero. It will become zero. So it is called unmagnetized. It is called unmagnetized. It is called unmagnetized. Clear about this? Okay. But when the same ferromagnetic material is placed in external magnetic field, yes. If it is placed in external magnetic field like this, in external magnetic field is zero like this, then yes, due to magnetic field, forces are acting on domains, torque is acting on domain, each and every domain, it will align in direction of magnetic field. It It will align in direction of magnetic field. Yes, due to magnetic field, the domains will merge into each other and they will make only one domain, having magnetic dipole moment in direction of magnetic field. Clear about this? So yes, it is behavior of ferromagnetic material in absence of magnetic field and it is in presence of magnetic field. Clear about this? Okay, and yes, in this case, as this ferromagnetic material is magnetized, inside this ferromagnetic material, magnetic field B increases because external magnetic field and magnetic moment of ferromagnetic material, they lies in the same direction. So yes, magnetic field increases. Yes or no? Yes, it is. Clear about this? So it is behavior of ferromagnetic material. Yes, clear? Okay. Now, what is effect of ferromagnetic material on temperature? See how? Yes, it is ferromagnetic material. In domain structure, it is domain structure. If I increase temperature of this substance, then what happens? This each and every domain, they starts getting distorting. It means this domain, this boundary is broken up. Okay, this boundary is broken up, and due to breaking of this boundary, this each and every atoms, they will have magnetic moment in random direction, independent of region. See, in this region they have same direction, in this region they have same direction, but when temperature increases up to a certain temperature, this each and every atom magnetic moment, they will become independent. Like this. In random direction. Okay? In random direction. Like this. And you know that. Okay? Remember last lecture? It is nothing but paramagnetic material. In absence of magnetic field. So yes, as the temperature increases, domain structure starts getting distorted. At a certain temperature, it is totally broken up, and each and every atomic magnetic moment is independent from one another, and ferromagnetic material is converted in paramagnetic material. Ferromagnetic material is converted in ferromagnetic material. Clear about this? So yes, above some temperature, this ferromagnetic material is converted in paramagnetic material. Okay, and the value of temperature at which it is converted in from ferromagnetic to paramagnetic, it is called Curie's temperature. And what is the relation between magnetic susceptibility and Curie's temperature? Chi m is equal to C1 upon T minus Tc, where Tc is called Curie's temperature and T, that is object's temperature. C1 is constant. So it is effect of temperature on ferromagnetic material. Okay, if it is ferromagnetic material, we increase its temperature beyond this Curie's temperature. It is converted in paramagnetic material. So you have to remember this point. So yes, what are basic differences between diamagnetic, paramagnetic and ferromagnetic that we have discussed. Now for this ferromagnetism, we have to discuss one most and last and the topic of this chapter, that is hysteresis. Hysteresis means what? It is ferromagnetic material like this. Okay, if I have one solenoid, if current is passing from solenoid and such ferromagnetic material is placed in solenoid, then what happens? That we will study. Okay, and we will plot one graph We will plot one graph which is called hysteresis cycle. Okay. Now next topic is hysteresis. What is hysteresis? Okay, hysteresis cycle. See, understand here. If we have one ferromagnetic material, in absence of external magnetic field, that is V0 is equal to 0. V0 is external. It is external magnetic field. It is external magnetic field. Okay, we know that what is configuration of ferromagnetic material. It is like this. This each and every dipole, they are aligned in random direction. So what is net magnetic moment? Magnetic moment is equal to 0. What is net magnetic moment? Magnetic moment is 0. And also resultant magnetic field. Resultant magnetic field inside ferromagnetic material B is also 0. Yes or no? Yes. Yes or no? Yes. Okay. Now we will think about one situation. If we have one solenoid, connected with, let's some battery. Okay. So yes, current is flowing. IF. Current flowing from solenoid is IF. Current flowing from solenoid is IF. Then we know that inside solenoid, magnetic field produced B0 is equal to, it is mu 0 and IF, or we can also say it is mu 0 H. It is mu 0 H. Yes or no? Where H is equal to it is NIF, or it is, we can also say it is mu 0 IF. Yes or no? Yes. So if we have one solenoid, inside solenoid, magnetic field produced is B0 is equal to mu 0 NIF mu 0 H. H, that is IF. So we can say in this solenoid, magnetic field is produced due to H. Magnetic field is produced due to H. Okay. Now, if ferromagnetic material is placed, inside this solenoid, then due to this uniform magnetic field, we know that this domain structure starts getting distorted. Yes or no? Boundaries will merge to each other, and at last we will have only one domain in the direction of magnetic field. Yes or no? Yes. So we can say this ferromagnetic material, okay, due to external magnetic field. External magnetic field means this ferromagnetic material is placed in solenoid. So this magnetic field is called external magnetic field for ferromagnetic material. Okay, due to external magnetic field B0, ferromagnetic material is magnetized. Clear about this? Is magnetized. Magnetized means net magnetic moment per unit volume produces. Net magnetic moment per unit volume produces. Clear about this? And yes, if it is magnetized, we will have some resultant magnetic field inside ferromagnetic material. Okay, we will have resultant net magnetic field B in core of material. Okay, so see, if I say current flowing IF is equal to 0, so H is equal to 0, then will this ferromagnetic material will be magnetized? No, it will be not magnetized. So what will be resultant magnetic field? 0. Yes, we know that when external magnetic field is 0, net magnetic moment is 0, and this ferromagnetic material resultant magnetic field is also 0. So we can say object is magnetized. Resultant magnetic field B B produces due to this H. B produces due to this H. So we can consider this B as output. We can consider this B as output, and we can consider this H as input. And now we will draw one graph of B versus H. Okay, one BH curve. One BH curve for ferromagnetic material. Okay, we will draw one graph of B versus H for ferromagnetic material. Okay, what about this graph? See here it is. Okay, we will draw one BH curve. We will draw one BH curve. See, here it is. Let it is H. It is B. So it is BH. Okay, it is BH curve. Now see, you have to remember, or you have to see each and every point. How? When current flowing from this solenoid is zero. How simple, no? Okay, when current flowing from this solenoid is zero, like this point O. It is point O. Okay, at point O. First, at point O. Let current flowing from solenoid IF is equal to 0. Yes or no? So H is equal to 0. H is equal to 0. So resultant magnetic field, external magnetic field in solenoid is 0. And now if I place this ferromagnetic material in this solenoid, will it be magnetized? No! So what is resultant magnetic field inside? What is resultant magnetic field inside the solenoid? B is equal to 0. Simple. Again, if current flowing from solenoid is 0, means H is equal to 0. H is equal to 0, so magnetic field produced inside solenoid is 0. No magnetic field, no magnetic field, no magnetization, no resultant magnetic field. B is equal to 0. So yes, when H is equal to 0, B is equal to 0. It is first point. It is first point. Clear? Now that current is flowing in this direction. Current is flowing in this direction. Okay, so yes, due to that current, yes, we know that as current is flowing, current starts gradually. Yes, it is not battery, okay? It is not battery, it is AC current. It is AC current. So as value of current increases, current increases, H increases. So magnetic field B0 also increases. External magnetic field increases. So dipoles will try to align in direction of magnetic field. Yes or no? Again, if current from solenoid increases, then magnetic field also increases. Due to this magnetic field, these dipoles in ferromagnetic material, they will try to align in direction of magnetic field. They will try to align in direction of magnetic field. Clear? So yes, resultant magnetic field inside magnet increases. So simple flow, okay? If IF increases, H increases, B0 increases, and B increases, and dipole will try to align in the direction of magnetic field, So yes, as H increases, B also increases. As H increases, B also increases. Okay, like this. At point B. As B increases, H also increases. Clear about this? Now, see, initially, when it is increasing with initial increase in current, there is no more change. In magnetic field. Why? Because, and why this graph is not linear? Initially it is like this. Means with increasing current, there is no change in magnetic field. Why? Because initially each and every domain, they will have magnetic moment in random direction. At point O, what is structure? Structure will be like this. This domain will have magnetic moment in random direction. As current increases, H increases, B0 increases, B increases. This dipole will align, try to align in direction of magnetic field. Initially, H value of current is small. B0 is not strong enough to deflect this domain. Okay, so yes, there is no directly proportional relation. Okay, at point A, what happens at point A? At point A, current in solenoid increases, magnetic field increases. Current in solenoid increases, magnetic field increases. Current in solenoid increases, magnetic field increases. At point A, magnetic field becomes maximum. Means what happens if it is direction of external magnetic field, each and every dipole will align in this same direction. So yes, resultant magnetic field is also in this direction. Yes or no? These magnetic moments, they are in this direction. So resultant magnetic field is also in this direction. And as B is maximum, it is called saturated. It is called saturated magnetization. Clear about this? Saturated magnetization. Okay, and yes, in this situation, this each and every domain will align. See, this each and every domain will align in the direction of magnetic field. That we will have only one domain. So yes, each and every dipole aligns in the same direction. We will have only one domain. Okay, magnetic field is maximum. It is called saturated magnetization. Clear about this topic? Okay. Yes, at this point, current IF is maximum. IF, or we can say H, is maximum. Okay. Now, yes. If we decrease current flowing from this solenoid, then also as IF decreases, external magnetic field also decreases. Yes. Now if IF decreases, H decreases, external magnetic field decreases. Yes or no? Yes. So yes, this each and every molecular dipole aligning direction of magnetic field due to this P0. Now if P0 decreases, then also this dipole will try to oscillate. So yes, they are deflected from their mean position. Means resultant magnetic field decreases. So yes, resultant magnetic field decreases. As H decreases, resultant magnetic field also decreases. But at this point, you can see from figure, at this point B, yes, at this point B, H is equal to 0, but B is not equal to 0. It means initially current is flowing from solenoid. If current is maximum magnetic field is produced. If I decrease value of current and if I reduces its value to 0, object is not demagnetized. It has net magnetic moment. It has some magnetic field, and it behaves as still magnet. Okay, so yes, when H is equal to 0, magnetic field is not 0. And yes, this magnetic field for which value of H is 0 is called retentivity. Value of magnetic field for which H is equal to 0. Value of magnetic field for which H is equal to 0 is called retentivity. Clear about this? Okay, so yes, at this point B, resultant magnetic field is not 0. Now if I reverse direction of current, then what happens? Now resultant magnetic field that is B0 inside solenoid will be in this direction. Resultant magnetic field in solenoid B0 will be in opposite direction. See, on origins, this side, right hand side, current is positive. On this side it is negative. So if I reverse direction of current, direction of magnetic field also reverses. If I reverse direction of current, direction of external magnetic field also reverses. Clear about this? And yes, see, initially all dipoles are aligned in this direction. Yes or no? Yes. If resultant magnetic, external magnetic field is in opposite direction, these two directions are now opposite. So yes, for some value of current, okay, here magnetic field will become 0 for some value of h, in opposite direction. So yes, at this point, resultant magnetic field will become 0. At this point, resultant magnetic field will become 0. Yes or no? Magnetic field becomes 0 for some value of h, and this value of h is called coercivity. It is called coercivity. Clear about this? Okay, the value of h for which B is equal to 0 is called coercivity. And see, in this case, again, magnetic field is 0. Initially during this phase, during point O, resultant magnetic field is 0. But see, these two are not same points. It means here ferromagnetic material is again demagnetized. It is again demagnetized, but with some another domain region. Okay, this domain region at point O and this domain region at point C. They are not same. Clear about this? In this case, these two domain region, they are not same. Domain region at point O and domain region at point C, they are different. So again, we will repeat this. At point O, it is unmagnetized domain structure in random direction. As H increases, B increases. At point A, magnetic field becomes maximum. Okay, magnetic moments, it is in direction of external magnetic field. We will have only one domain, means we can say ferromagnetic material is magnetized. And as it is maximum magnetic field, it is called saturated magnetized. Clear about this? Now if H decreases, magnetic field decreases. At point B, H is equal to 0, but magnetic field is not 0, and that value of magnetic field is called reflectivity. Now if I reverse direction of current flowing from solenoid, means if I reverse direction of H, the magnetic field inside ferromagnetic material, reduces, because magnetic moment and magnetic field, they are in opposite direction. So yes, it decreases, and at this point, resultant magnetic field inside ferromagnetic material becomes 0. It is again demagnetized, but with different domain structure. Clear about this? Okay. Now, if I increase current IF in reverse direction, then obviously this B0 in reverse direction increases. Yes or no? H in reverse direction increases, and yes, now this each and every dipole will try to align in this new magnetic field. They will try to align in this new magnetic field. So yes, as H increases, B0 increases, resultant magnetic field inside pole increases. Okay, at this point, as now result external magnetic field is in this direction. At this point D, this each and every domain will align in this direction. They will have only one domain. But in this direction, resultant magnetic field is produced in this direction, means in opposite direction to that. See, if this point and this point, they are opposite to each other. Clear about this? Clear about this? So yes, this point D, it is also called saturated. It is also called saturated magnetization. It is also called saturated magnetization. Clear about this? So yes, you have to understand from point O to point D. At point D, again it is magnetized. Clear? So O demagnetized with this structure. Point A magnetized with this structure in one domain. At point C again demagnetized. At point D again magnetized. Okay. Now next points are simple. Okay, if now we decrease value of current, then magnetic field also decreases. Magnetic field also decreases. At this point, again, magnetic field is not zero, but value of current is zero. And if again we reverse direction of current, that magnetic field increases. Clear? So yes, this part is simple. We have to increase current, increase current. Then we have to change direction of current, and current increases. Okay, so it is one complete BH curve. Okay, for a ferromagnetic material, for one complete cycle. What is meaning of complete cycle? Yes, we have one solenoid. In solenoid, initially current is zero. Then current is flowing in one direction. Increases, becomes maximum. Current then decreases, becomes zero. Then reverses its direction, increases, maximum, decreases, zero. Then again reverses its direction. So for such cycle, we have to plot a BH curve. And this BH curve is called hysteresis cycle. It is called hysteresis cycle. Clear about this? So yes, again, it is one important topic. You have to read this each and every point, and yes, you have to remember two definition. Value of magnetic field for which H is equal to 0 is called refractivity. Value of H for which magnetic field is 0 is called coercivity. Clear about this point? Yes. Area enclosed by BH curve. One important MCQ. Okay. Area enclosed by BH curve gives heat energy produced per unit. Clear about this? So yes, you have to remember this. Area enclosed by BH curve gives heat energy produced per unit. Clear about this? Okay. So yes, it is hysteresis that you have to remember. Okay.